Well, hello everyone. I wanted to give you a different sort of introduction into the final chapter on logarithms. What I'm going to do is look at a article that appeared in the newspaper, and then I'm going to massage the math that appeared in that article into chapter 9 form, that is, into logarithms. I just want you to sit back and don't sweat the math right now. There's going to be plenty of times ahead to focus on understanding and the techniques involved. For right now, just think of this as an overarching introduction to the ideas of logarithms. So sit back and follow along with me if you would, please. What I have right here is an article from Sunday's newspaper by Greg Hansen. It appeared in the sports section. And what it was about was the connection between Tucson and the Kentucky Derby. It turns out it's rather phenomenal. One of the horses that's going to be favored Saturday is looking at Lucky, which is trained by a UA alumnus, Bob Baffert, whose farm is down there in Nogales. Now, also, really quite interesting, is the idea here that looking at Lucy is owned by Tucson auto dealers Paul Whiteman and Carl Watson. But not only that, the horse is going to be ridden by Tucson native Garrett Gomez. So lots of connections, and that's why Greg Hansen felt compelled to write this article. But what I found interesting was the next paragraph, where Paul Whiteman is quoted as saying, "Hey look, every year 38,000 foals are born in the horse racing industry, and 20 of them make it to the Kentucky Derby. Think of those odds. It's mind-boggling." And of course he's right, 20 out of 38,000 is really long odds. So what I thought we'd do is look at those numbers and play around with them a bit. Now, in probability, the main idea is, well, the total idea of probability is built on the idea of a fraction, in which the bottom of the fraction is the universe of all possible outcomes. And in the case at hand, we're talking about the universe of all foals that are born every year in the horse racing industry, and that's 38,000. And the top of the fraction in probability is always the desired outcomes, and of course it has to be smaller than the bottom of the fraction, which is all possible outcomes. And in the case at hand, we're talking about 20 of those foals that 3 years later will become contestants in the Kentucky Derby. So there is the fraction of interest, and what I've done is simplify it down to 1 out of every 1900, which would seem to be the end of the line. But when I was taking probability and statistics, I didn't like to just leave a problem like that. And so I came up with this hack where I would get a more visceral feel for long odds. And what I would do is compare them to flipping a coin and getting consecutive heads on all my flips. Let me flesh this out for you. I'm going to introduce that idea, and you'll see how we'll transition to logarithms with it. So to flip a coin and get a head with one flip, the mathematics looks like this. And this is all quite apparent to you, I know. The idea here is that the total possible outcomes is 2. You can get a heads or a tail with one flip. The desired outcome is a head. I want to get a head with that one flip. So 1 out of every 2 times we're going to achieve the desired goal of getting heads. Now what I've done here is rewrite the fraction showing the exponent on the 2, and there's a reason for that. As I build this model, that exponent's going to become critical. Now I want to do it 2 flips of the coin. And what are the odds of me flipping a coin, same coin twice, and getting 2 consecutive heads? The mathematics of that looks like this. 1/2 times 1/2. The chances of getting a head on the first flip is 1/2, and the chances of getting a head on the second flip is 1/2. And we multiply those together. Now that's called the probability or product rule of probability. And I'm not going to explain that idea. It's very fundamental, and any probability course you take, you'll get it within the first few days of the course. But it's multiplication and not addition. So the odds of getting 2 consecutive heads are 1/2 times 1/2, or 1 over 2 squared, or 1 over 4. 1 out of every 4 times. But again, I'm showing the exponent down here because, as you can see, I did 2 flips and the exponent was 2. With 1 flip, the exponent was 1. And so quite naturally, as I go to 3 flips and wonder what are the odds of getting 3 consecutive heads, the mathematics should be showing us a pattern. So it's going to be 1/2 times 1/2 times 1/2, or 1/2 to the third, or 1/8. So 1/8 times that I flip a coin 3 times, 1/8 times that I do this experiment, I should get 3 consecutive heads. And again, you can see the three attempts, the 3 flips, are modeled as the exponent on the 2. So if I asked you what are the odds for getting 4 flips, 4 consecutive heads, you would say, I think, 1/2 to the 4th. And if I asked you for the odds of getting what are the odds of getting 5 consecutive heads with 5 consecutive flips of a coin, you would say 1/2 to the 5th. And in general, what you would say, I hope, is 1/2 to the nth. Well, what I want to know is how many consecutive flips in which I get heads do I need to emulate the odds of having a full run in the Kentucky Derby, which we know is 1/1900. And so there you go. There's the equation that brings us into Chapter 9. And what I want to do is solve that equation. So let me bring it over here and let's get to work on it. Now, you know when the tops of the fractions are the same, that means the bottom of the fractions have to be the same. So I could rewrite this like this. And we have a more classic equation, no fractions. And so how do I solve for n, though? I've put it in red because I want to focus all your attention on it. How do we solve this? How do we isolate n from this equation? And the answer is there's no known way up to this point, to this moment of our algebra course. There's nothing in the past that will free that n from being an exponent. There's no moves we can make on it. And so how is it done? How do you solve for n? And the answer is it's a ruse. It's a notational ruse invented by mathematicians, and it looks like this. We create a new entity called logarithms. Now, I'm going to read that right side a couple of different ways. I'm going to read it formally. Formally, this is read out loud as log to the base 2 of 1900 is equal to n. Log to the base 2 of 1900 is equal to n. And informally, the way to wrap your head around logarithms, and I'll have lots of practice for you on this, is to actually rethink what you see here. For me, what I say, this is the exponent. Notice that n is an exponent. See it? It's right there. It's an exponent. N is an exponent. So the left side is an exponent. That means the right side has to be an exponent. This is the exponent. You raise 2 to get 1900. What exponent do you raise 2 to get 1900? In a sense, that's exactly what this equation up here says. What is the exponent you raise 2 to get 1900? N is the exponent you raise 2 to get 1900. So you'll have lots of practice of rethinking and rewriting in your mind what this notation means. Essentially, it means this right here is an exponent. It doesn't look like an exponent, but this is the exponent you raise 2 to get 1900. Okay, well, what about a number? What number is that? And I'm going to bring in the calculator here to solve that. Notice my calculator has the key right here, log to the base 2. It also has log to the base 10, which we'll be dealing a lot with. And it also has this key, which is known as the natural log. This is a shorthand for log to the base e. We'll be dealing with that in future sections. For now, though, this is the one we want. And what I'm going to do is put in 1900. And when I hit this key, this is going to give me the number that you raise 2 to get 1900. When I hit that, there is your answer. You raise 2 to 10.8918, and that actually continues on. It's an irrational number. It goes on forever and never repeats. You raise 2 to that number to get 1900. Okay, let me drag in that solution right here and also show you the roundup. N is approximately equal to 11. Okay, so what does this mean in terms of the Kentucky Derby, raising a full, and coin flips? Essentially, N is 11 here. We're talking about 11 for right here. 11 coin flips have to come up heads in a row. I have to flip a coin 11 times in a row, and it has to come up heads every time to emulate the odds of getting a full in the Kentucky Derby, which is 1 out of 1900. So for me, that was a way of feeling these numbers. I know it's a very difficult chore to flip a coin 11 times and get heads every time. How difficult is it? It's as difficult as getting a horse in the Kentucky Derby. Okay, I hope that helps. As an overview, like I said, much more in the days ahead. Be talking to you soon.